So we saw yesterday that in the simple Langevin model for diffusion of particles in a fluid, the equation is mv dot plus m gamma v is equal to a white noise 8 of t. If this is a Gaussian white noise, a random process with a delta correlation, a Markov process which is stationary and has a delta correlation, then the velocity v also turns out to be a Markov process and its conditional density turns out to be the Ornstein-Uhlenbeck distribution. So we saw that this implied, and you can show that this implies and is implied by the fact that the conditional density, the velocity is v at time t, given that it was v naught at some instant of time t equal to 0, this quantity this was given, the normalized distribution was given by 2 pi k Boltzmann t 1 minus e to the minus 2 gamma t. This is a time dependent normalization factor multiplied by a Gaussian function which is minus v minus the average value whole squared divided by the variance which is twice k Boltzmann t 1 minus e to the minus 2 gamma t. This was the Ornstein-Uhlenbeck distribution, which starts as a delta function at v equal to v naught at t equal to 0 and asymptotically approaches the Maxwellian distribution, the usual Gaussian distribution corresponding to thermal equilibrium as t tends to infinity. Now of course once you are given this and the fact that v is a Markov process, which we have not proved but I am asserting that it is so, then all probability distributions connected with v are known. N time distributions are completely known because everything could be written for a Markov process in terms of this conditional density alone. Okay. But the interesting thing is this density also obeys a differential equation which looks like the diffusion equation but has an extra term, and we will discuss that a little bit today, and that equation and this stochastic differential equation are equivalent to each other. The equation obeyed by this p is delta p over delta t, and it is called the master equation for the probability conditional density of a Markov process. In this case this master equation is a second order partial differential equation and it happens to read equal to gamma delta over delta v times p plus gamma k b t over m d2p over dv2. So this equation together with the initial condition, so p which is a function of v and t, so p of v and t with the initial condition p of v0 equal to delta of v minus v naught and a certain set of boundary conditions, because it is second order in space in v we need boundary conditions and natural boundary conditions, namely p of vt goes to 0 as v tends to plus or minus infinity, specifies a unique solution, and that is this distribution. So the unique solution of this second order partial differential equation with this initial condition and this set of natural boundary conditions happens to be the Ornstein-Uhlenbeck distribution. One can prove this rigorously. You can solve this equation explicitly by a variety of methods, but we are not interested in that at the moment, but this is where the Ornstein-Uhlenbeck distribution appears from. This particular equation, the master equation for the conditional density, this equation is the first example of what is called a Fokker-Planck equation. This is a class of equations for a specific kind of Markov process which I will mention in a minute, and it is perhaps the first example or one of the first examples of a Fokker-Planck equation. This equation for the velocity was actually written down by Lord Rayleigh and it is sometimes called the Rayleigh equation, okay. But its common parlance it has become known as the Fokker-Planck equation, because it is an example of a class of equations which are labeled as the Fokker-Planck equations. Now we found also from this that the velocity was correlated exponentially. So we found that the velocity v at time 0 v of t average, v of t1 v of t2 was a function only of mod t1 minus t2. I can shift the origin and call 0 one of the arguments here. In equilibrium this turned out to be kbt over m e to the minus gamma mod t minus t prime. This is the way you define for a Markov process a correlation time. What you do is to take this process, if you have a stationary Markov process, and let me denote xi for general stationary Markov process, you take this quantity xi of 0, xi of t, take its average value, that is the correlation function, provided the mean is 0 at all times. If the mean is not 0, you should subtract the mean at every instant of time. So let us even do that. Let us write the most general formula down. The actual correlation function c of t would be defined as xi of 0 minus average psi, which is time independent if it is a stationary process, the average of that multiplied by this deviation from the average, this quantity here would actually be the correlation function. But you can easily see, it is easy to check, that this is the same as the average value of xi of 0, xi of t minus mod average xi whole squared. So this thing here is in fact xi of 0, xi of t minus average xi whole squared. So it is a generalization of the variance of the process, that is all that the correlation does. Let us for the time being, for the case of v this was 0, so let us simply drop it, and then you can define a correlation time in the following way. So you take this quantity xi of 0, xi of t, you normalize it by xi squared, that is the value at t equal to 0. This function is guaranteed to start at 1 at t equal to 0, and then in general it would drop off to 0 as t tends to infinity. Could drop off very slowly, but here it drops off exponentially fast, not always guaranteed, but in this problem it drops off exponentially fast. So if you took this quantity and you integrate it over all t, you get a quantity of dimensions time. So 0 to infinity of this, if this integral converges, you get a certain characteristic time in the problem, and this is what you would call the correlation time of the process. So that is the way. Pardon me? For any observable. If this is a random process, if this is a stationary random process, then this is a way of extracting a time scale in the problem, the time scale on which the system loses memory. Some observable, yes.
Will the correlation be same for any observable?
That is a good question. This question is, if I look at this problem and I look at the velocity correlation time, is that the same as the correlation time for say the position or anything else? We will see, that is an interesting question. We will see what happens to the position in a minute. For the velocity it is so, this is certainly going to give you a correlation time. Pardon me?
What is xi?
Is this quantity? This is xi squared average, so that this is normalized to unity, otherwise this quantity has the physical dimension of the square of xi, whatever it be. I want to extract a time from it, so I remove this quantity gets rid of the physical dimensions of xi, and it is something which would typically look like this. This function here would start at 1 and die off, and I am saying this quantity here, this area under the curve, is actually got the physical dimensions of a characteristic time scale. It is not easy, it is not hard to prove that if you took this in the present instance, this would imply a tau correlation time equal to gamma inverse. It trivially follows that you simply get 1 over gamma as the correlation time of the velocity. Now the next question is, very nice, we have something for the velocity. What about the position? What happens to the position? Something very complicated happens to the position. The fact is, it turns out that I must really look at the motion in phase space. As we know in dynamics, you must look at things in phase space. So since I am looking at one component of the velocity, the x component say, I should really look at the pair x comma v, and then I should not even be talking about p of vt, I should be talking about the joint density in phase space of x vt given say some initial position v0 at t equal to 0. So it is this quantity that I should look at, and I should ask how does that evolve as a function of time. It turns out you can write a Fokker-Planck equation for that quantity that would correspond to writing an equation for the probability density corresponding to the pair of variables here. So I would write x dot equal to v and v dot equal to this. It would look like a dynamical system except that it has got random components here, and then I could write a probability density of that kind and then ask what is the equation obeyed by it. It also satisfies a Fokker-Planck equation, which is somewhat more complicated, but we could actually write it down quite simply. Pardon me? Yeah, the statement is dynamics happens in phase space, as we know from our experience with dynamical systems. So we are talking now about a random velocity of an individual particle, the x component of the velocity say. I should really talk about the position and the velocity together, because that is what constitutes a point in phase space, right. So I should really write down a coupled set of equations, and here is the coupled set of equations. X dot is v and v dot satisfies this equation, which is random, this eta is random. Corresponding to this stochastic differential equation, I have a probability density in phase space which is given by rho of x vt. This is the probability density, or when multiplied by dx dv, this gives you the probability that if a particle starts at x naught with velocity v naught at time 0, it is found in the range v to v plus dv in velocity and x to x plus dx in position at time t. This quantity satisfies the Fokker-Planck equation also, which is more complicated than this equation. In fact, we could write this equation down, let me do so. That is the Fokker-Planck equation in phase space, and it is actually not much more complicated than this.
Not just limited to velocity as such, right? If this is going to be a Fokker-Planck equation for one dimension, it's going to be for two dimensions.
Yeah, I should write it down, really I should write down not this, but I should write down r, I should write down v, and I should write down r naught, v naught. So let us do this in several steps. I should really finally aim at writing rho of r v t given r naught. Pardon me? No, the motion occurs, I look at particles in this room, they are moving in 3-dimensional space, but each of them is moving in a 6-dimensional phase space, one particle phase space, it is 6-dimensional.
My question is, can this be generalized to any dynamical system, or is it only for Hamiltonian system?
It is not a Hamiltonian system at all. This thing is not a Hamiltonian system, it is right away gone from that. There is no way you can produce this friction in a Hamiltonian system. I put this model in phenomenologically, and I put in a random component here. So we move to a stochastic dynamical system now, which is in fact dissipative. But
enforcing the condition that should be even dimensional.
no, I am not saying anything like that. I am saying that every particle has the particle motion occurs in phase space, that is all I am saying. I need to have equations of motion which I write down should be for all the dynamical variables, and the position and the velocity or the position and the momentum, they determine the state of the particle at any time. So it is not Hamiltonian, it does not have to be Hamiltonian at all. I am not writing any Hamiltonian down at all, but the idea of phase space is more general than that of Hamiltonians, as you know. If this particle had other internal degrees of freedom, then the dimensionality of the corresponding phase space would change, but it is a point particle, so its position and momentum.
You are limiting yourself to something like r comma. Why do you have r comma v? You can have some k vector comma t. Why do you have a
You mean why don't I have, what else could I have here?
some one vector k vector comma t given
What's the k? It's got,
some dimension, some dimension.
it's got to be a physical observable pertaining to the point particle. What are the physical observables pertaining to a point particle at any instant of time? Right? That be its position and momentum, that is about it. It is true that if I have this particle in, if it turns out that there are velocity dependent forces, it turns out there are other degrees of freedom interacting with it, it turns out for example that its basic equation of motion is 6 dimensional or 7 dimensional, I would have to include those extra terms. But as long as I have forces which are conventional kinds of forces, we know that the position and momentum are sufficient here, or in this case the position and velocity. So this is the sort of quantity I would look at, but let us first do this for one dimension and then I write it down immediately in arbitrary in 3 dimensions. The equation turns out to be delta rho over delta t plus v delta rho over delta x equal to whatever we wrote on the right hand side, gamma delta over delta v, v times rho this time, plus gamma k dt over m d2 rho over dv2. This is the Fokker-Planck equation in phase space. Nothing much has happened, nothing much has happened. You have added this term here, in fact you can intuitively guess where this term comes from. What does this remind you of? Yes, in fluid dynamics, yeah, v dot del, so it reminds you exactly of that, it is a convective derivative. So the left hand side is really the total time derivative of rho in that sense. So that is all that happens, and this has a very complicated solution. If I write this down with initial conditions, P of x v 0 is delta of v minus v naught delta of x minus x naught, and I use natural boundary conditions saying that rho vanishes as x tends to plus minus infinity, v tends to plus minus infinity, then the solution turns out to be a fairly complicated distribution, turns out to be a Gaussian jointly in x and v. So it is a multivariate Gaussian distribution. I am not going to write that down right now. Now how could you generalize this to rho of r comma v comma t? That is also obvious, almost obvious, let us say. So what would the general equation be in 6 dimensional phase space? How would it change? This remains the same, and not surprisingly this becomes plus v dot the gradient of rho, gradient with respect to r, of rho, and on the right hand side out here you actually have gamma times the gradient with respect to v dotted with v rho. It is the divergence of this. This means the components of this are the partial derivatives with respect to the 3 velocity components, and this term here becomes del with respect to v squared of rho. That is the full Fokker-Planck equation for free particles in the absence of an external force in phase space, and the solution is a generalized Gaussian in all these variables. You can use a matrix method to solve this equation, but it is a little intricate and we will not do that here. So you can generalize these to actual motion in any number of dimensions, okay. But our purpose now is not to do that. We go back to this set of equations, the Langevin equation, and ask what can we say about the position of the particle. We know all we need to know about the velocity because its conditional density is given by the Ornstein-Uhlenbeck distribution. What can we say about the position of the particle? How far does it move in a given time? So let us see what happens. So we could start with the particle moving from the origin at t equal to 0 or at any point x naught, and then let us find out what it does. So I know that x of t minus x of 0 is equal to an integral from 0 to t dt1 b of t1. This is a definition of the displacement, and let us call this delta x of t. Now I would like to find out What is the mean square displacement? So all I have to do is to take the square of this and take the average in equilibrium. So what does that give us? That gives us 0 to t dt1, 0 to t dt2, and then you have a v of t1, v of t2 in equilibrium, no external force. But we already know what this is. This is the exponential that I wrote down, and therefore you can compute this number, right? You can actually calculate this number fairly straightforwardly, because all you have to do is to put in that exponential there and compute it. So let us do that. A little trick involved here, because remember that this quantity was k Boltzmann t over m e to the minus gamma times modulus t1 minus t2. There is a modulus there. In other words, in the t1 t2 plane you have to integrate 0 to t for t2 and a t1 here. This is the line t1 equal to t2, and you have to integrate over this whole square here. But the function here is symmetric with respect to the function there, because it is a function of the modulus. The value at any point here is equal to the value reflected on this line. So we could as well write this as equal to twice the value in one of the triangles. So I could write this as twice the value from 0 to t dt1, and this goes from 0 to t1 dt2 k Boltzmann t over m e to the minus gamma. Since t1 is bigger than t2, I could just write this as the t1 minus t2 without the modulus. And which triangle am I integrating over? I am integrating over t1 from 0 to t, and each time t2 is restricted, it goes from 0 up to this quantity here. So it just goes up till there. Now that is the integral I am doing. And that is a trivial integral to do. It is very simple, and the result is the following. So you end up with delta x of t whole squared is equal to, it turns out, 2 k Boltzmann t over m gamma, m gamma squared, because I am going to do two integrals here, and the k Boltzmann t over m comes from here, and then it is an integral which gives you gamma t minus 1 plus e to the minus gamma t. And that is the result. What can you say about the displacement now right away from this result? This quantity is the mean square displacement, and it is a function of the time. What sort of process is the displacement now? If the mean square value depends on time, what can you say about this process? Is it stationary or it is non-stationary? Exactly. So that is the first problem. It is not even a stationary process, unlike the velocity, whose statistical properties were independent of time, and therefore the mean square and so on were all independent of time. This process is not even a stationary random process. So its correlation function is going to depend on both time arguments and is not a function of this, of the difference of the two alone. So if I compute delta x of t1, delta x of t2, it is a function of both t1 and t2. And how does this function look? As a function of t, if I plot delta x of t whole squared. Exactly. So it is clear that asymptotically this term and this term are going to dominate over this, and this is a straight line which intersects at t equal to 1 over gamma here. So it is clear there is a straight line of this kind with some slope, and this function, look at what happens for t very small, gamma t much less than 1. This goes like 1 minus gamma t, which cancels both these things, and then you got a gamma squared t squared. So it starts off like a parabola, and then it asymptotically hits this value here eventually. So it is clear that this function looks like this, and this line here, its ordinate is 2d 2 whatever it is, 2k Boltzmann t over m gamma t minus 1 over gamma. It is a straight line, and that is the asymptote. So it behaves linearly for sufficiently long times, but at short times it is quadratic, and then in between it has both the exponential as well as the linear term, and it is not a stationary process. X of t is not a stationary turns out it is not even Markov. But there is one case where things simplify. Where have we come across the statement that the mean square displacement of a diffusing particle increases linearly with the time? This is a famous diffusion equation prediction. So if you write the diffusion equation down for the positional probability density function, then we can prove directly from that that the mean square displacement increases linearly with time. But this is saying something else. It is saying it is not linear, it is only linear for sufficiently long times. This thing here is gamma inverse, and if t is much bigger than gamma inverse, which is the velocity correlation time, then the mean square displacement increases linearly with time. So it is giving us a very important input. It says the diffusion equation, which I would normally naively write down from Fick's laws of diffusion, are valid only at sufficiently long times. How long? Times much longer than the velocity's memory time, correlation time. So that is telling you something beyond the diffusion equation. So now let us backtrack and write down the diffusion equation and see what that implies and what sort of stochastic equation that implies again. So let us go back to our phenomenological, the usual phenomenological description of diffusion is in terms of two conditional densities. So let me call, I need to use another symbol for it, so let me use the symbol P, a little script there, for the position of a particle at time t. This is the positional probability density. And what do you say about this? It is like if I take a diffusing species and I write the concentration as a function of position and time, I would write the two laws of Fick, the Fick's laws for diffusion. The first one is just conservation of matter, and the second law tells you how things move. So the equations, if you recall, for the concentration of a species at time t, the equations, Fick's laws are delta c over delta t equal to, on the right hand side, this quantity is equal to, it is equal to minus the divergence of a diffusion current. That is the continuity equation. That is Fick's first law. It is just the conservation of matter continuity equation. But the second law says something dynamic. It says under suitable conditions the current J of RT is proportional to the negative gradient of the concentration. So the current moves from the region of higher concentration to the region of lower concentration. So it is equal to minus the gradient of the concentration, and the coefficient here is called the diffusion coefficient D. And when you put both these guys together, of course you end up with the diffusion equation, which says delta C over delta T equal to D del squared C. That is the famous diffusion equation. The positional probability density of a single particle in one dimension, now moving in one dimension, satisfies the same equation. This is almost by definition, and therefore it implies that we have the diffusion equation delta P over delta T equal to D d2 P over dx2. That is the diffusion equation. So we set aside the Langevin model, we are not going to think about it for the moment. We come to this, we look at this diffusion equation and ask, can we say something about the motion of the particle from here? Well, I need to specify initial conditions and boundary conditions before I am through. So let us start with the simplest initial condition. Let us assume that on the x axis the initial concentration is at x equal to 0. So this delta function at the origin. So let us say that P of x0 is equal to delta of x. So at t equal to 0 it starts at x equal to 0. I could shift the origin as I please, but let us choose the origin to be at x equal to be at the initial position of the particle. What are the boundary conditions you would like to put? Well, I certainly like to have this, I would certainly like to have the total concentration to be finite, and the equivalent of that here is minus infinity to infinity dx P of x comma t equal to a finite quantity, and if it is a probability density function then it is equal to 1 for any t greater than or equal to 0. I would certainly like to normalize this probability. So it should be some non-negative function which is whose total area under the curve is unity and which starts as a delta function at t equal to 0. What is the necessary condition for this integral to exist? It is an integral which runs from minus infinity to infinity, the entire x axis. So when would that exist? Well, this function must be integrable of course, but it must vanish at the endpoints, otherwise this integral does not exist. It must vanish sufficiently rapidly at the endpoints, but certainly it must vanish. So the natural boundary conditions, natural BC P of x t tends to 0 as mod x tends to infinity, as x tends to plus or minus infinity. On both ends I would like it to vanish. Given this initial condition and those boundary conditions, this equation has a unique solution, and we know the solution. The famous diffusion equation solution is in fact P of xt is equal to the exponential of minus x squared over 4 dt, and there is a normalization constant which is square root of 4 pi dt. This is the famous Gaussian solution. It simply says that as time goes on this becomes a Gaussian, then it widens out and eventually dissipates down completely. The area under the curve remains 1 at all times, but this curve broadens, finally P vanishes at every point, but the total area is 1. That is the fundamental Gaussian solution to the diffusion equation or the heat conduction equation. These are all identical equations. Well, for one thing we can find the value of the mean value of x, or the mean square of x, etc. You can in fact do that without solving this equation, but once you have it you can write it down. How do you find the mean value of x? How do you find x of t average from this equation without solving the equation? What would you do? Well, I would like to compute x of t equal to an integral dx x times p of x comma t. If this is normalized to unity, then this is the definition of the mean value. So let us do that. Let us multiply both sides of this equation by x and integrate over t, over all x. So what happens? I multiply this by x on both sides and integrate from minus infinity to infinity. I have integral minus infinity to infinity dx x times delta over delta t p of xt, this quantity, is equal to d times an integral minus infinity to infinity dx x times d2 p over dx2. But remember the t dependence comes entirely from here, so I can actually pull this out. Once it is integrated over x, this is just a function of t alone, and I can pull that out, and since it is a function of t alone I can simply write it as d over dt. But what is this quantity equal to? By definition it is the mean value time t. So it says d over dt of x of t is equal to this, and the obvious thing to do is to integrate by parts. So if I integrate this by parts, this gives me d times x delta p over delta x at x equal to minus infinity plus infinity minus d times an integral minus infinity to infinity dx times the derivative of this function with respect to x, which is 1, and the integral of this, which is delta p over delta x. So it just gives me delta p over delta x this fashion. But this is 0 because we would like all moments of this quantity of x, I would like the mean value, the mean square value and so on to be finite, which means that p of xt must not only go to 0 as mod x goes to infinity, but must go to 0 faster than any negative power of x, otherwise that moment would diverge. Therefore, since this goes to 0 faster than any negative power of x as x goes to plus minus infinity, this quantity goes to 0. So this is gone, and what does this do? This gives you just the surface terms p at plus infinity and p at minus infinity, which are 0. So that is gone, and therefore we find this is 0. Which implies that this quantity is a constant. But if I start at the origin at t equal to 0, this is 0 at t equal to 0, and since it must remain constant, it is 0 at all times. So just telling you physically the fact that if you start with a symmetric initial distribution and let diffusion occur without bias, the average would still, the distribution would remain symmetric at all times, the average would remain 0 at all times. So this is identically 0. What happens to the mean square displacement? That is not 0, of course, that is non-trivial. So I would like to find x squared of t, which is this, and I start by finding x squared on this side, I multiply by x squared. So I have d over dt of x squared of t. On the right hand side, this is what we are going to get. I am going to put an x squared here and integrate over x. The first term, the surface term, will have an x squared dp over dx, which goes to 0, and the next term will be a minus d times an integral minus infinity to infinity the derivative of x squared, which is 2x. So there is a twice, and then there is a dx, and then an x delta p over delta x. The derivative of x squared, the integral of dp over dx, which is this, and now I integrate by parts once again. So that gives me equal to minus 2d x times p at minus and plus infinity, that vanishes once again, and then a plus sign 2d times the derivative of this, which is unity, and the integral of this, which is p itself integrated, but the integral of p is 1 because it is normalized. So it is just this, it finally leaves you with just 2d. Which implies at once that x squared of t equal to 2d, t plus a constant, but at t equal to 0 this is 0, and so the constant drops out, and you end up with this famous result that the mean square displacement in diffusion is linearly proportional to time, and the coefficient of proportionality is 2d in each dimension of motion. In 3 dimensions, if I computed r squared, it would be average x squared plus average y squared plus average z squared, which would give me 6 dt. Now how does that tally with the result there? This thing here is certainly not a linear function of t, except in the limit gamma t much bigger than 1, and these two must match. Therefore, in the diffusion regime, so we could call this the diffusion regime, T much greater than gamma inverse. In that regime, x squared average of T equal to 2 dt. We got something even more interesting. If that is the case, I must then equate this phenomenological coefficient d, which just got put in by hand, with what we got from the microscopic model here, and that implies that 2 dt here must be 2 dt there, and that immediately tells you this 2 is sitting here and the gamma cancels and you end up with d equal to the diffusion coefficient is not arbitrary, it is related to the dissipation in the system, and it is related in this particular fashion. This is another expression of the fluctuation dissipation relationship that I talked about the last time. So diffusion actually tells you how things spread out, how fluctuations act on the system, and gamma tells you how the dissipation in the system acts, and there is a connection between them. This is also related to the viscosity of the fluid. So now you could go back and ask, what does this mean? What sort of stochastic equation does X satisfy in order for this to happen? And for this we need to know a little bit about the connection between stochastic differential equations and the corresponding master equations, the Fokker-Planck equations. I will write that relationship down without proof, and it is as follows. The relationship,
Sure, the microscopic equation converges to this linear form only when T is greater than T is
only, yes, that is what happened. I mean that particular microscopic model.
one case. Are you sure that that's the only case in this problem?
No, not at all, that is only a model as it stands. So we have no guarantee of this at all. Finally you have to test against the experiment whether the model is successful or not. So the statement made is the following, and now by hindsight we can mention what in this particular problem what the resolution of this whole business is. The time between collisions, the time of interaction between two molecules is of the order of 10 to the minus 15 seconds, that is the sort of electromagnetic interaction time. The time between collisions is of the order of a picosecond or less. The next time scale is the velocity correlation time, which under normal circumstances for the kind of fluids we are talking about would be of the order of microseconds. So diffusion, the diffusion equation would be a good approximation to the transport phenomenon on time scales much greater than microseconds, that is it. So there are lots and lots of time scales in the problem, they are well separated from each other, which is why this trick works finally. And of course in a dense fluid under different conditions and so on, things can get much more complicated. The velocity is not given by the simple Langevin equation. The point I want to make here from the point of view of dynamical systems is that for a given stochastic differential equation you can write down a Fokker-Planck equation for the conditional density, and it is as follows. So if you have a random variable xi and it is given by a first order stochastic differential equation of the kind xi dot is some function of xi, we do not care what, some function which gives you the drift of this thing, plus a white noise of this kind eta of t, let me call it zeta of t, multiplied by perhaps a function of xi once again, and this is the stochastic differential equation. Where zeta of t, where f and g are given functions and zeta of t is a Gaussian delta correlated stationary Markov process with 0 mean. So we will make that assumption, zeta of t is a Gaussian white noise with 0 mean, 0 and zeta of t prime equal to delta function of t minus t prime I have absorbed whatever constant sits here in this G here. If this is the stochastic differential equation obeyed by the random variable zeta xi, then this implies xi of t is a Markov process whose conditional density satisfies a Fokker-Planck equation of the following kind. P of xi t satisfies delta p over delta t equal to minus delta over delta xi f of xi p of xi t plus 1/2 g squared of xi this is the Fokker-Planck equation satisfied by P. This is rigorously provable. So the moment you have a random variable driven in this fashion by white noise, Gaussian white noise, stationary Gaussian delta correlated Markov process with 0 mean, then you are guaranteed that the output process P is a Markov process whose conditional density satisfies this equation. This is generally given the name the Fokker-Planck equation, and what we had is a special case. In that case the equation we had for V, if you recall, was V dot equal to minus gamma V plus a white noise which is eta of t over 1 over m times this. So G was essentially a constant in that problem. So once we have this, let us go back and ask, what about the diffusion equation? What kind of process was that? Well, the diffusion equation said delta p of xt over delta t was equal to d2p of xt over delta x2. So it corresponded to a situation where f was 0, this term did not appear at all, and this term here was a constant which is given by G. Okay. So it is quite clear that the stochastic differential equation x dot is given by a white noise on the right hand side, and it is just square root of 2d times zeta of t. So if you put G equal to square root of 2d, then half G squared is in fact d, and that is what we had. So f equal to 0, G was just a constant, and this tallies with what we already know. If this is a white noise, its correlation time is 0, and we already saw that the displacement behaves, its mean square displacement behaves linearly in the diffusion regime when t is much bigger than gamma inverse. In other words, when the time scale is much larger than the correlation time of the velocity, or another way of saying it is on time scales compared to which the velocity correlation time is 0 and acts like a white noise. So really these two things are not contradictory at all, but there is a consistency condition which connects one to the other here. In fact, that can be generalized. It does not have to be, and this is the final thing I want to mention, it does not have to be the Langevin model at all. You could in fact start from very general considerations and ask what does the diffusion equation, what does the diffusion constant do, and that is not hard to see, and that is the final thing I am going to talk about. So all we have to do is to start with this statement that the displacement in a time t is in fact the integral of the velocity over that time, and then if I compute the square of this and average, this gives me this quantity 0 to t dt2, and then I have v of t1 v of t2 average, and if the velocity is stationary in equilibrium, that is all I want. In other words, the energy does not change at all, everything is in thermal equilibrium, then independent of what the form of this quantity is, I could in fact simplify this whole thing. So the first step is to write this as, this is a symmetric function, so it is a function of mod t1 minus t2, this fashion. So the first step is to write it as twice the integral from 0 to this of this guy, and write it as f of t1 minus t2. Now what have we done? Well, here is t1, here is t2, and this is 0 to t, 0 to t, and I am integrating in this fashion. But I could equally well integrate by interchanging orders of integration in this fashion. So if you interchange orders of integration here, this becomes 0 to t dt2 on this side, and this integral t1 is always bigger than t2, so it runs from t2 up to t1, up to t2, sorry, up to t, that is right, dt1, and then this function of t1 minus t2. And now I change variables to t1 minus t2, inside to t1 minus t2. And what happens to the lower limit of integration? This becomes a 0, and then this integral is trivial to do, one of the integrations is trivial to do, and you end up with a result which is twice an integral 0 to t dt2, if you like, or let me call it dt prime, t minus t prime in this fashion, and then inside is v of 0 v of t prime. This quantity is expected to start at 1 and decrease to 0, and the integral runs up to t. What is the asymptotic t going to infinity behavior of this? Well, this term is going to dominate, and this limit will go up to infinity. The parts where t prime becomes comparable to t would be damped because they go down here. So it is clear that the t going to infinity limit of this, the asymptotic behavior of that, is in fact this quantity for sufficiently long times goes to twice t times an integral from 0 to infinity dt prime v of 0 v of t prime. But if you insist that this should be equal to 2 dt, by definition it gives you a basic formula for the diffusion coefficient. So it implies that eventually the diffusion coefficient is intimately connected to the velocity correlation, and independent of the model, d is integral 0 to t dt prime 0 to infinity. I might as well drop the prime here, v of 0 v of t in equilibrium. So it says the transport is determined by equilibrium fluctuations in thermal equilibrium, the fluctuations of the velocity. This has a name, it is an example of what is called a Kubo-Green formula. In the Langevin model, this was kT over m e to the minus gamma t, and of course that gave you d is kT over m gamma, but that was specific to the model, but this is much more general. All you need is that this integral converges. Actually it does not even have to converge, you can show that the d, if the process is diffusive and not super diffusive or anything like that, then this d is actually the analytic continuation of the Laplace transform of this to s equal to 0. So you could put in an e to the minus st, then it is the Laplace transform of the velocity correlation, and if you after doing the integral go to s equal to 0, that is the diffusion constant. So this is in fact the beginning of the subject of non-equilibrium statistical mechanics, but our interest here was from the point of view of dynamical systems, and what I wanted to show you was that even if you include noise, then the formalism changes a little bit. It is more convenient to talk about phase space densities or densities now, like the invariant measures we talked about earlier, to talk about time dependent probability density functions, write equations for them and solve them, and you get all the averages that you need here. And of course you could ask more complicated questions like what happens if you have a combination of deterministic and random components to the dynamics. Things get harder and harder, but the formalism is well laid out. So the moral of the story is eventually you have to use statistical methods, you have to write down equations for from either from or from other inputs, either from the dynamical equations or otherwise you have to write down equations for the distribution functions, the probability densities or the measures, and then after that find statistical averages of the quantities that you want. And then there may be internal consistency conditions like the one we found for D here, which you have to impose. In general they are not. If the things, if the random is, the noise is totally different, it is an external source, there may not be such consistency conditions. So very few general lessons, but there are some pointers as to what one should do in such cases. With that maybe I should stop here.